Hello, good evening, everyone. So this is the second live problem solving session for the course Aqueous Corrosion and Sensor. I'm Jeet. So just since it's the beginning, just a second session. So I'll go over the basics again. Get over the three slides. So my session will be on Tuesday from 6 to 8. I'll briefly recap the topics covered in the video lectures of that week and then try to go over the practice problems. And then go over the previous week's assignment. And at the end, if people have doubts, you can ask me. So today we'll cover lecture 4th and 5th. I'll update this sheet in case there's any shifting of the slots. But right now, these are the dates in the yeah, it's in every Tuesday. You already have the meeting link. The YouTube videos. These sessions will be recorded and uploaded to YouTube. This is the link for my YouTube channel. You can watch them. The slides of the session will be uploaded on this Google Drive link, and you can have access. I think I'll let's see if I can shorten the URL. It's difficult for someone to type. Um, okay, the shortened link. Okay. So I'll briefly go over what was covered this week. First, how we calculate the rate of corrosion. So suppose we had an example of zinc. So we have zinc and some zinc rod and solution. So then plus two electron. Also Zn zinc. Select standard standard equilibrium potential is minus 0.3. So on the surface of the metal, making the solution, water will be zinc plus 2 ions and zinc. So on the surface, both the oxidation and redox reaction, oxidation and the reduction reactions are both taking place. So oxidation, this is the reduction reaction, where zinc plus 2 electron becomes zinc, and oxidation half zinc loses 2 electron becomes zinc plus 2. So at equilibrium, both these reactions would happen at the same rate. So there would be no change in the zinc plus 2 ion concentration in the solution, and the mass of the zinc rod would remain the same. That is at the equilibrium. However, if you offset the equilibrium, maybe by changing the Z plus 2 ions or applying some external potential. So here we have E, this is our minus 0.3 0.763. So there was something called exchange current, I naught. So for every each of these reaction, it's involving some charge transfer, right? The zinc plus 2 is gaining some electrons, becoming zinc. So whenever you have some charge transfer, movement of charges, you also have current, right? Current is just movement of charge. So due to this charge transfer, you are getting this current. So at equilibrium, the redox uh, current density and the oxidation current density would be both equal. So net there would be no current exchange, but if you just see one, there would be some current density in one direction. If we just consider one of the reaction. So at 0.763, you have some current density. We call it I naught. This I naught is same for Zn plus 2 to Zn and would be equal to I naught for Zn to Zn plus 2. Okay. Now, if you apply some external, oh, this is log of I. Now, if you apply some external potential to this metal, you can either reduce the potential or increase the potential. Increase, I mean, make it more negative or making it less negative. To make it less negative, it will go like this. Make it more negative, it will be something like this. So if you take any point, suppose this point, you've increased this point, you've increased the negative potential. So suppose this is minus 0.863. Here you will get some current. So here you're actually at this situation we had equilibrium. The rate of oxidation was equal to rate of reduction. However, here now the reduction reaction is winning, is more favorable. So we get metal plus 2 or zinc plus 2 gets electron and becomes metal. And on this side, if we reduce the negative potential, actually if it increasing the potential, then the metal is getting oxidized to metal plus 2 electron. And each of these potential, you'll get some current density. And through this current density, you can calculate the corrosion rate. So a lot of questions you are asked. What is the change in the potential? Like how much external potential should be applied to for this rate of corrosion, or like this is the rate of corrosion and you need to suppress it. So potential should you apply? Yeah. Yes. Yeah. This increase or decrease, changing this potential from the equilibrium potential is also called polarization of the electrode. Here, this is acting as electrode, we are making a zinc electrode. So if you disturb it from the equilibrium position, you are polarizing electrode.
So, won't there will be two TEFL line in this equation? One cathodic line of acid
Yeah,
reduction.
this here I'm just showing for the metal. So in solution, if you have like this, uh, there should be another reaction taking place. There cannot be any charge accumulation. So maybe hydrogen is getting reduced or oxygen is getting OH minus is getting oxidized or something like that. So there would be a complementary reaction. We'll see this like in few slides. Yeah. So wherever those two like reactions meet, so we'll have this for one species, and there'll be another cathodic and anodic part for the other species. Wherever they intersect, this is your the rate of corrosion. So this is just for a single species which is getting oxidized or getting reduced. Right? So for more things, the slope of this line, this is actually the TEFL equation. So we usually write this as over potential. So eta, and this is log of current density log I, and this is the E naught. This is the anodic and cathodic. So the slope of the anodic is their beta A, or TEFL slope, sorry, beta A, and for the cathodic branch you have beta C. Okay, so these are the TEFL slopes and how this the relation between the overpotential and the current density is given by the TEFL equation. So if you go just go to another uh, potential for the electrode, that will be over potential would be like E minus E naught. Right, this is E. This is E. So your eta anodic. This is cathodic actually. So this is E A E C. Eta anodic will be E A minus. Sorry, E applied minus E cooling. So E A minus E naught is equals to your TEFL slope beta A log I divided by I naught. I naught is the equilibrium exchange current density. Yeah. And similarly for anodic part, the cathodic part, you have E cathodic minus E naught is equals to beta minus beta log I or log I naught. There beta, since the slope is negative, you get minus sign here. These are TEFL equations. Next, this is also how the TEFL slope is related to charge transfer coefficient. I didn't see any questions right now, but in this assignment, but yeah, it's the relation RT alpha NF. Alpha is your transfer coefficient, which is usually alpha is equals to 0.5. So he has claimed like how the energy versus reaction coordinate graph looks, and depending on how symmetric or unsymmetric it is, the alpha can be greater than 0.5 or less than 0.5. If it's completely symmetric, yeah, the alpha will be 0.5. So, as you mentioned, there would be both anodic and cathodic reactions taking place at the surface. So, the total current, this is just a Butler-Warner equation. Again, I don't know if it will be coming up in this course or not right now. It's alpha. So this is the anodic part. This is the cathodic current. Alpha. T. So this is the Butler-Wolver equation. And so there was one more thing, if how diffusion can control the rate of reaction. So at the electrode surface, you have both reactions taking place, right? Metal plus two electron, and H plus maybe plus two electron, this H2. Both these reactions are taking place at the metal surface. So this is given by the Butler-Warner equation, the current density. However, if you have some other species, like this is hydrogen is getting reduced, right? You may have oxygen getting reduced. So here H plus ion actually diffuses quite well. However, if you had oxygen which was getting reduced, so oxygen plus two electrons, um, H minus, you have some H plus ions. Yeah, so it's O2 plus H2O plus 4 electrons and 4 OH minus. This is oxygen reduction reaction. Okay, so in case of oxygen, the oxygen would need to the oxygen at the surf near the surface would get consumed, right? So if you just if the oxygen bulk concentration, bulk O2 concentration. So suppose this is the bulk concentration before any reaction is taking place. Concentration of O2 at bulk. Near the surface, you see a dip in the concentration, which is since the oxygen is getting consumed. So the oxygen would need to diffuse toward the electrode surface as it's getting consumed. So here you'll see diffusion limited reaction current. Uh, the current you get is diffusion limited current. So You may increase the potential as much as you want, but since there's no oxygen to react, this is a metal surface. Since there's no oxygen to react and take the electrons from the metal, uh, metal, right? So the reaction would, the current won't increase more than the limited by diffusion, right? The diffusion can be given by the Fick's law, because J is equals to minus d dc by dx. This is the length, this is the concentration difference, d is diffusion constant, and this is your flux rate of diffusion. You can go over the derivation and the so for corrosion especially, the diffusion current plays an important role. I'll just copy the slides. Okay. So this is the when you derive the diffusion limited current, this is the equation you get. Okay. And if you increase the rate of diffusion somehow, maybe by increasing the temperature or mechanical stirring or whatever, your diffusion limited current density will increase. No matter how much electrode potential you're changing, after a point it reaches a saturation point, and after that, changing the electrode, if you go even lower magnetic side, the current doesn't change much, so it's limited by the diffusion. So now, if you have water flowing in a pipe, so water has oxygen dissolved in it, and suppose at this patch corrosion is taking place, so there is a fresh supply of oxygen with the flowing water, which is promoting the corrosion. So in flowing pipe, you get more corrosion. Depending on the velocity of the water, the corrosion rate will decrease, increase or decrease. So in real life conditions, like actually there's a mix control, so the rate of reaction, the current current density is governed by both the diffusion and the cathodic and anodic reaction, the charge transfer taking place. So you can eta diffusion 2.303 RP in the log 1 minus I naught by I limiting. Okay. The lower potential versus the current diffusion limited current density. Eta total would be just for cathodic reaction, so beta cathodic log of I over I naught plus your eta diffusion system. This would be your total over potential. Then there was a mixed potential theory. I Wagner. Say if we have multiple reactions taking place, as you mentioned, there was metal. The metal is getting oxidized. So we have two reactions taking place. Metal, metal becomes metal plus 2 and plus 2 electrons. Hydrogen plus H plus 2 electron. CH2. So we have overall reaction metal plus twice H2. Sorry, H plus. Yes, metal plus 2 plus H2. So here both these reactions are taking place. Here hydrogen reduction reaction takes place at 0 volt at standard potential. This maybe has some standard equilibrium potential of minus 0.5, which maybe. So when both these reactions are taking place, the value of the equilibrium potential, the potential will be, for the reaction would be somewhere in between these two values. And that can be calculated by the Mixed potential theory. So it has some assumptions. First is any electrochemical reaction. So this is an electrochemical reaction. It can be broken into two or more partial reactions. Right. This is the first assumption. Split into two or more partial reactions. Second is there's no accumulation of charge. By this, it means that suppose you have only one reaction taking place, which is metal becoming metal plus 2 electron. If only this reaction was taking place, your solution would get uh, uh, metal plus 2 ion concentration in the solution would keep on increasing. Your solution is becoming positively charged, and your rod would have leftover electrons from what the metal gave out. It would have negative charge. So this cannot happen. Simultaneously, there should be another reaction taking place which accepts this electron and um, reduces itself. And if you're reducing plus 2 solution metal positive ions in the metal, the other reaction would give you negative ions in the solution, balancing out the charge. So there's no net accumulation of the charges. Uh, this basically says rate of reaction, rate of oxidation is equal to rate of reduction. Okay. Now, how do you calculate the corrosion rate? You have your metal bar inside the solution. You have some ion concentration inside the solution. This is your metal. There's some metal plus 2 ion concentration. Drawing the Tafel plots again. Log of I and E. more potential beta. For hydrogen, the standard reduction potential is zero. So here is hydrogen. It would have some exchange current density, right? Because so if you increase the potential, you're oxidizing the hydrogen. So half H2 becomes H plus plus electron. So anodic reaction. And if you reduce the potential, you're getting the cathodic reaction. Here is H plus plus electron becomes half H2. Okay. Similarly, for the metal, we'd have some equilibrium potential. This is zero. We have P M plus M. Right. Again, you have both cathodic and anodic reactions taking place. So if you increase the potential, you have a cathodic reaction taking place, anodic reaction taking place, which is metal plus 2 plus 2 electron n if it's n electrons, and your cathodic reaction, which is metal plus n electrons, you get metal. And wherever these two currents become equal, so we saw there could be no accumulation of charges. So at this point only the corrosion is taking place at this point. It's here the rate of the cathodic current, which is hydrogen reduction reaction, and an anodic current, which is the oxidation reaction of the iron. Both currents become equal, so there is no accumulation of the charge. So this point is your I corrosion. Okay, and the potential at which this corrosion is happening, E corrosion. The corrosion potential. This is the corrosion potential and the corrosion current density.
सर मेरा इसमें एक क्वेश्चन है, एक डाउट है।
हाँ जी।
ये जैसे जब इंटरसेक्शन पॉइंट है उस पे आपका एक रिएक्शन का कैथोडिक करंट, मतलब जो हाइड्रोजन रिएक्शन है उसका कैथोडिक करंट
हाँ
और जो मेटल रिएक्शन है उसका एनोडिक करंट बराबर हो जाता है।
हाँ जी।
बट जैसे सर ये जो कोरोजन पोटेंशियल है, ई कॉर जो लिखते हैं,
हाँ,
ये ई कॉर क्या रिजेंबल करता है? मतलब पूरे इलेक्ट्रोड पे ये पोटेंशियल आ जाता है या मतलब ये किस चीज का
अगर
पोटेंशियल होता है ई कॉर?
ये आप एक स्टैंडर्ड हाइड्रोजन उसके इस मेटल को अब आप जो करोजन के ड्यूरिंग, अब इसको अगर हाइड्रोजन रेफरेंस सेल के रेफरेंस इलेक्ट्रोड के साथ कंपेयर करोगे, यहाँ पे हाइड्रोजन एक सोल्यूशन में एक हाइड्रोजन मैंने इलेक्ट्रोड भी लगा दिया, तो अब मैं जो सरफेस पे ये जो मेरे को पोटेंशियल जो दिख रहा है मेरे को इसमें, वो ई कॉर के बराबर होगा।
ये एवरेज आउट पोटेंशियल होगा पूरे सरफेस का। जैसे मान के चलें कि एक कैथोडिक साइट है, एक एनोडिक साइट है। कैथोडिक साइट पे हाइड्रोजन रिएक्शन हो रही है, एनोडिक साइट पे मेटल ऑक्सीडेशन रिएक्शन हो रही है। तो
हम्म,
जब हम उसको इलेक्ट्रोलाइट में इमर्स करते हैं तो पोटेंशियल एक दूसरे को अप्रोच करना चालू करता है क्योंकि मेटल शॉर्ट होता है और
हाँ
आपका कैथोडिक करंट और एनोडिक करंट एक दूसरे को अप्रोच करना चालू करता है। इंटरसेक्शन
हम्म,
पॉइंट पे कैथोडिक एनोडिक करंट बराबर हो जाता है।
हाँ।
ई कॉर क्या दोनों साइड का बराबर होता है? जैसे एनोडिक साइट है, कैथोडिक साइट है, दोनों का पोटेंशियल ई कॉर है या एवरेज आउट पोटेंशियल ई कॉर है?
हम्म, इस रिएक्शन का तो ई कॉर पे आप एच प्लस आयन कॉन्सेंट्रेशन यहाँ पे कुछ चेंज हो जाएगी, क्योंकि एच प्लस कंज्यूम हो रहा है। तो जो स्टैंडर्ड इस रिएक्शन की राइट जैसे दिस इज
मेरा सर
योर।
डाउट मेरा जो
हाँ,
डाउट
तो
है
दोनों
सर ये है
रिएक्शंस
कि
की पोटेंशियल बराबर जो अपने लिखते हैं ना, E इज इक्वल्स टू ई नॉट माइनस आर टी बाई एन एफ एंड देन योर इस केस में प्रेशर एच टू डिवाइड बाई कॉन्सेंट्रेशन एच स्क्वायर। तो ये जो E है, इस पॉइंट पे ये ई कॉर बन गया। ई कॉर।
सर जैसे ये वाला ई जो आप लिख रहे हैं सर, ये तो बेसिकली इक्विलिब्रियम पॉइंट पे हो गया जहाँ पे एक्सचेंज करंट डेंसिटी है, और जहाँ पे आपका मतलब जो इनिशियल स्टार्टिंग पॉइंट है। मैं फाइनल ई कॉर की बात कर रहा हूँ जहाँ पे कर्व इंटरसेक्ट कर रहा है, जो कि पोलराइज्ड पोटेंशियल है।
तो अ,
ये
सर
जो
मेरा
नस्ट
अंडरस्टैंडिंग,
इक्वेशन
हाँ
बोल रहा है
मेरी
कि
अंडरस्टैंडिंग है जैसे इनर्स्ट इक्वेशंस, एक तो ये है, दूसरी हो गई जो मेटल की होगी, मेटल प्लस, मेटल से मेटल प्लस राइट।
हाँ सर, बट ये तो
बिकॉज
इनिशियल पॉइंट के लिए से जो स्टार्टिंग पॉइंट है, मतलब स्टार्टिंग पॉइंट पे अगर हम कंसंट्रेशन चेंज करते हैं
हाँ,
या
तो
हम
यहाँ पे
फास्टर स्पीड में चेंज
कंसंट्रेशन चेंज
करते हैं,
होगी यहाँ पे।
तो
इसकी
इनिशियल
सर,
पॉइंट के लिए तो वैलिड होगी, बट जब पोलराइज होना चालू होगा सर और इंटरसेक्शन पॉइंट पे आएंगे तो ये इक्वेशन सर वैलिड होगी नस्ट इक्वेशन इस पॉइंट के लिए, ई कॉर के लिए।
हाँ, तो इक्वर पे वहां पे जो एच एच प्लस आयन की कॉन्सेंट्रेशन होगी उस पॉइंट पे जो सरफेस के पास में होगी वो इससे ही निकालेंगे अपने इनर्स्ट इक्वेशन से।
बट ये सर ये ई कॉर आएगा या ई इक्विलिब्रियम आएगा, जो स्टार्टिंग पॉइंट है वो इस इक्वेशन से आएगा या ई कॉर आएगा सर?
आई थिंक एक और आएगा क्योंकि जो स्टार्टिंग पोजीशन में हमारे पास कोई रिएक्शन नहीं प्लेस हो रही, रिएक्शन टेक प्लेस नहीं हो रही थी राइट। तो हाइड्रोजन आयन कॉन्सेंट्रेशन पूरे सोल्यूशन में बराबर था राइट। एंड सरफेस पे आपका हाइड्रोजन आयन कंज्यूम होंगे प्रोड्यूसिंग हाइड्रोजन गैस राइट। तो उससे आपकी ये जो ई इक्विलिब्रियम पोटेंशियल है वो शिफ्ट हो जाएगी ई कोर की तरफ, क्योंकि आपका हाइड्रोजन आयन कंज्यूम हो रहा है। सिमिलरली दूसरी तरफ देखोगे तो ये प्लस होगा, दूसरी तरफ मेटल आयन कंसंट्रेशन मेटल सॉल्यूशन में कुछ होगी, बट एट द सरफेस इलेक्ट्रोड आप देखोगे तो देयर वुड बी इंक्रीज इन द मेटल आयन कंसंट्रेशन। आप इस पॉइंट पे जाएंगे तो वो भी, उसकी पोटेंशियल भी इक्वल की तरफ जाएगी। तो अगर इस केस में देखेंगे तो ये वैल्यू इंक्रीज होगी ताकि ई ई दिस बिकम्स इक्वल टू इक्वल। और दूसरी तरफ इसका मेटल का देखोगे, मेटल मेटल प्लस टू माइनस समथिंग, तो ये वैल्यू इंक्रीज होगी ताकि दोनों जाके बराबर हो जाए इक्वल के। तो वहां पे आप मेटल के कंसंट्रेशन एंड हाइड्रोजन एंड कंसंट्रेशन इसी इक्वल से निकालोगे।
मतलब जैसे सर इनिशियल पॉइंट है, इनिशियल पॉइंट जो स्टार्टिंग पॉइंट है वहां
दिस
पे क्वेश्चन लगाई,
ये वाला।
उसके बाद आगे वाले पे जो जो स्लोप एक बार पोलराइज होना चालू हुआ, तो वहां पे
हाँ,
या तो टेफल्स इक्वेशन या बटलर वॉल्मर इक्वेशन लगा करके हम उस पॉइंट पर अराइव कर सकते हैं, ओवर वोल्टेज जो भी हो रहा है।
इस जो
नस्ट
जहाँ
इक्वेशन
पे
सर वहां पे अप्लाई होगी एक और पे सर, मेरा मतलब एक तो ये डाउट है, दूसरा ये डाउट है सर कि अगर पूरे सरफेस का पोटेंशियल बराबर हो गया, इक्वल हो गया, तो फिर
हाँ।
मतलब पोटेंशियल डिफरेंस एग्जिस्ट ही कहाँ कर रहा है जिसके थ्रू करंट फिर फ्लो हो रहा है? मतलब अगर पूरा सरफेस एक बराबर पोटेंशियल पे आ गया, इक्वल पे पहुंच गया, तो फिर करंट कैसे फ्लो होगा अगर पूरा क्योंकि करंट का बेसिकली जो है वो पोटेंशियल डिफरेंस से ही आ रहा है।
ओके, तो हम, तो अगर यहाँ पे हाइड्रोजन जो मैंने, अगर इसके अराउंड मैंने सील कर दिया इसको, जस्ट क्लोज जो एरिया है, तो वहां पे इस पॉइंट पे जाके जो रिएक्शन रुक जाएगी राइट।
सर सील कर दिया तो बहुत तेज पोलराइज करेगा, मतलब स्लोप्स काफी तेज होंगे और फिर रिएक्शन आगे जाके जब हाइड्रोजन स्टार होगा तो रुक जाएगी।
हाँ, तो हाइड्रोजन इसकी कंसंट्रेशन जब यहाँ पे आके फिर देख रहा हूँ,
सर मतलब नर्स्ट इक्वेशन क्या इक्विलिब्रियम पॉइंट से एक बार हम शिफ्ट होते हैं, मतलब बेसिकली पोलराइज होते हैं, पोलराइज करते हैं तो इक्विलिब्रियम से शिफ्टिंग होता है, क्योंकि वहां नेट करंट फ्लो होना चालू हो जाता है। इक्विलिब्रियम पे क्या
हम्म,
होता है, एनोडिक और कैथोडिक करंट बराबर होता है, जो कि एक्सचेंज
हाँ
करंट है। एक बार हम
हाँ।
इक्विलिब्रियम से शिफ्ट होना चालू करते हैं और हम जाते हैं इक्वार की तरफ, जो कि पोलराइजेशन प्रोसेस है, जहाँ पे नेट करंट आना चालू हो जाता है। तो नेट करंट के केस में क्या नर्स्ट इक्वेशन लगेगी?
इसमें भी तो जो कैथोडिक और एनोडिक करंट बराबर हो रहे हैं इस पॉइंट पे।
सर बराबर हो रहे हैं, बट सर ये तो बटलर वार्मर
डिफरेंस
इक्वेशन
भी।
से जाएगा ना सर।
अ, मैं चेक करके बता रहा हूँ यहाँ पे नर्स्ट इक्वेशन वैलिड। क्वेश्चन क्या है, नर्स्ट इक्वेशन वैलिड है जब।
नर्स्ट इक्वेशन सर, मेरा अंडरस्टैंडिंग मतलब मेरा डाउट है कि नर्स्ट इक्वेशन केवल केवल इक्विलिब्रियम पॉइंट पे वैलिड है।
ओके।
इक्विलिब्रियम पॉइंट से एक बार शिफ्ट होना चालू किए, नेट करंट फ्लो होना चालू हुआ, एक्सचेंज करंट से शिफ्टिंग हुआ, तो फिर बटलर वॉल्मर इक्वेशन या टेफल्स इक्वेशन, मतलब उन दोनों में से टेफल्स इक्वेशन बेसिकली बटलर वॉल्मर का ही एक फॉर्म है सर, तो
ओके
वो एप्लीकेबल होगी इसको अराइव करने के लिए जो आप ई कॉर पे जा रहे हैं।
ओके ओके। मैं चेक करके बताता हूँ फिर। ये है इसमें। And we shift away from the application.
ठीक है सर। एक सर और डाउट है, ये जो आपने सर
हाँ
ग्राफ
हाँ।
बनाया है इंटरसेक्शन वाला, नेक्स्ट स्लाइड पे सर, लास्ट स्लाइड पे आ
ये
जाइए सर, ये वाला जो
ये
ग्राफ है, ये अच्छा पोटेंशियल वर्सेस लॉग आई है या ओवर वोल्टेज वर्सेस लॉग आई है?
अगर ये पोटेंशियल वर्सेस होना चाहिए। ओवर पोटेंशियल में ये उसमें सब्ट्रैक्ट करना पड़ेगा ये, राइट। तो
हाँ
ई
जी,
माइनस
अदरवाइज तो
ई
वो फिर
नॉट,
जीरो से ही
हाँ।
चालू होगा पोटेंशियल।
हाँ तो जीरो से कर रहा हूँ तो ई से ही या ई होगा ओवर पोटेंशियल। इंडिविजुअल हाँ अलग अलग दिखा रहे हैं तब ओवर पोटेंशियल लिख सकते हैं। जीरो को शिफ्ट करते हैं। आई थिंक कोर्स स्लाइड में तो इतना ही कवर था, ये लास्ट स्लाइड थी। I'll go over लास्ट वीक का असाइनमेंट एंड देन इस वीक के असाइनमेंट में व्हाट क्या थोड़ा बहुत हिंट क्या कर सकते हैं लास्ट वीक असाइनमेंट। ओके सो क्वेश्चन इज फाइंड द इक्विलिब्रियम पोटेंशियल फॉर CO plus 2 to CO for concentration of 0.01 mole and you're given the standard potential equilibrium potential for the reaction CO plus 2 to CO. Yeah. So you have CO plus 2 electron becoming CO and squeeze standard reduction potential C plus 2 plus 0 and 0.277. And you're given concentration of CO plus 2 is equal to 0.01 mole. So here E becomes E0 minus 0.059 divided by number of electron 2 into log of activity of CO तो 1 है 1 over concentration of CO plus 2. So we are given minus, this is given as minus 7, 0.052 into log of 1 over 10 to the power minus 2. So this becomes 10 to the power 2. Log of 100 is 2. So minus 0.277 minus 0.059 2 into 2. So we should get minus 0.36 volt. So options we have. These are the options. So versus SHC, first option would be right. Okay. I think yeah, it's 70%. Second question. Second question was a piece of zinc is immersed in copper sulfate solution. At what concentration ratios of zinc and copper ions? Zinc will stop corroding. Given the standard reduction potential for zinc or copper. Okay. You have your reactions. Zinc plus 2 electrons, and then E naught for this reaction is minus 0.76 volt. Okay. Okay, let's write the next equation for this. E is equal to E naught minus 0.059 by 2 log of 1 over Zn. Zn plus 2 ion concentration. So we are given we get E is equals to E naught minus 0.76 minus 0.059 divided by 2. I'll take the minus sign inside, bring the minus out on log using plus 2 concentration. This is your first reaction, equation. The second equation for the copper reduction reaction, Cu plus 2 plus electron, which is Cu, for reduction potential for Cu plus 2 to Cu is given as 0.399 volt. So we are writing the mass equation for this. E is equals to E naught minus 0.059 divided by 2 log 1 over Cu plus 2 and concentration. This becomes E is equals to minus 0.399. Again, I take the minus side out, sign out. That's 0.059 divided by 2 log of copper ion concentration. For corrosion to stop, the standard equilibrium potential for both this reaction should become equal. To the second equation. Stop corrosion. And Ez plus 2 that then becomes equal to equilibrium potential for copper reduction. Whenever this becomes equal, your corrosion will stop. So what you get is minus 0.76 plus 0.059 by 2 log of zinc ion concentration is equals to 0.399 plus 0.059 divided by 2 log of copper ion concentration. So I can bring this side minus 6.7 to that side. We have 0.059 by 2 log of that and concentration minus 0.059 log of copper ion concentration. There's a 0.39 plus 0.76. So 0.059 divided by 2 log of Zn plus and concentration minus log of Cu plus 2 and concentration is equals to it's given differently 0.39 6 1.5 almost 5.59. Yeah, so log of log minus array, so you can take them in plus 2 copper plus 2 iron concentration is equals to 1.19 into 2 divided by 0.059. This becomes equals to 39.28. Now taking log to the other side, becomes Zn plus 2 ion concentration divided by Cu plus 2 ion concentration is equals to 10 to the power 89. So Zn, yeah, Zn plus 2 approximately 10 to power 39. So A would be correct. Yeah, the exact value. Okay, you take the like write the exact value 10 to power 0.28 to 10 to power 39. 10 to power 28 would be like 1.6. Two eight, 128. So this is approximately 1.9 into 10 to power minus 39. I think in the solution it's थोड़ा सा फर्क है 39.22 लोगे तो you'll get 1.66 under A. Next is question 3. So what is the equilibrium? What is the equilibrium potential for Fe, Fe2, Fe plus 2 oxidation of cell at 25 degrees Celsius when the concentration of Fe plus 2 ion in the solution is 10 to power minus 6 moles or 10 to power minus 5, 4, and 4 moles or 10 to power minus 2.5 or zero point 0.1 moles. You're given the reduction potential of Fe and Fe plus 2. And I'll solve one or two of these. Yes, so we're given we're given Fe plus 2 electron gives Fe. This standard potential is given. 0.441. A part and the equation first. So equilibrium potential at any other concentration, Fe is equal to Fe is equals to E naught plus 0.0591 divided by 2 log of. So here I've already included this. Issuing like this 1 over Fe and concentration. Okay. This value you're given minus 0.44. Minus sign I'll take. Uh, this is Fe to the power minus 1, so minus 1 I'll take out, so this is plus 1, 0.0591 divided by 2 log of Fe in concentration. Fe plus 2 concentration. Okay, so first question, next part. We're given Fe in concentration is 10 over minus 6. We get Fe E naught E is equals to minus 0.44, 0.51 to log of 10 to the power minus 6. Okay, so minus 0.44 plus 0.0591 divided by 2 into minus 6 minus 3 minus 0.44 becomes 0.591 into 2. Minus 1.7 0.1773. Add these two, get 44. We get 0.6 minus 0.673. So either C or D is correct, and then I think I can third one maybe for C option. Let's see. Again, E is equals to minus 0.44 plus 0.0591 divided by 2 log of concentration, which is 2 minus 2.5. Minus 10 to the power minus 2. 10 to the power minus 2.5. Minus 0.44 plus I'll take minus of 0.0591 into 2.5 to straight away calculate the final value. 0.591 into 2.5 divided by plus 0.4. We can use minus 0.518 minus 0.518 or 73. So D would be correct. Just substitute the other two values and we get the other two values too. I want to it here. Okay. Next question is we're asked pH. Okay. And the pH of what will be pH of water if following solution are added? First one 0.01 molar HCl. Cl. So this would dissociate into H plus and Cl minus water. We get 0.101 molar concentration of H plus ion. So pH, you know, is equals to minus log of H ion concentration plus ion concentration. So H ion concentration will be given minus log of 10 to the power minus 2, right? 10 to the power minus 2 is equals to minus into minus 2, that's 2, pH 2. Second, little different, like 0.1 mole H2SO4, you'd get 0.01 into 2 moles of plus H plus H plus ion concentration and 1 mole 0.01 molar H sulfate solution, sulfate ion. Right. So H plus ion concentration becomes 0.02 mole. Again, pH is equals to minus log of 0.02 this becomes 2 times 10 to the power minus 2 divided minus log 2 multiplied by if the log given multiplication, add them, log of 2 plus log of minus 10 to the power minus 2. And this is just in case you have to do it in exam. So 10 to the power minus 2 minus of log 10 to the base 2 is 0.3 log of t. Right, 0.3 301. This becomes minus 2, 2. So your pH is 2 minus 0.301. The minus of plus 1.6. Definitely 1.7. So pH is 1.7. There goes 2, there is 1.7. Third is in case of NaOH. given 0.01 normal NaOH. Because it only gives one OH minus, so the molarity is also same. Concentration of OH minus is equal to 10 to the power minus. So if you know, or in aqueous solutions, pH, the concentration of OH minus, the product of these two, and H plus is 10 to the power 14. If you take log of these two, log of minus 14, log of OH minus concentration plus log of H plus ion concentration is equal to minus 14. So if you just put the minus beside, so minus log of OH minus log of H plus is equal to 14. So this you can write POH, so we have pH plus pH is equal to 14. So we can calculate first POH and then calculate the pH. So POH is equal to minus log of OH minus concentration. So minus log of 10 to the power minus 2 is to 2. So this reaction, this equation, pH equals to 14 minus 2 is to 12. Okay. Next question. What is the pH? What is the partial pressure of H2 that is required to stop corrosion of nickel in one normal solution of nickel sulfate with pH is given as 7 and you're given the reduction potential for nickel. Okay. So two questions. So nickel is getting converted to nickel plus 2 electron, and your other half reaction is the hydrogen reduction reaction plus 2 electrons gives H2 gas. For this reaction, you're given 43%. Okay. Nickel plus 2 electron. The equilibrium potential for redox reaction is given nickel E not equals to 2 plus minus 0.25 volts. So you can calculate the equilibrium potential given here Anode equilibrium potential is given. Equilibrium potential E is equals to E naught minus 0.0592 and log of 1 over nickel ion concentration. Okay. This is here minus 2.5. I'll take the minus out. 0.0591 divided by 2 log of L plus a normal. So since it's one normal, so nickel ion concentration is half. And they get minus 0.25 plus 0.05 log of 0.5. This will get minus 0.358. Equal 0.59. And the other reactions, this is for the oxidation of, for reduction of oxidation of reduction of next page for reduction of you get E is equals to E naught, I think 0 minus 0.0591 divided by 2 log of I write the plus 2H plus 2 electrons, yes, X2 partial pressure of H2 divided by HN concentration. Clear. Okay, 0 minus 0.0591 divided by 2 log of, I take that minus sign inside, log of H plus ion concentration square divided by CH2. So to stop the corrosion, these two should be injected in nuclear potential for both the reaction arcs should be equal. Equal. Whenever both the reduction potential of both these species becomes equal, the corrosion would stop. Okay. minus 0.258 equals to 0.0591 divided by 2 log of H plus ion concentration we are given. Means pH is equals to 7, H plus ion concentration is equals to 10 to the power minus 7. So 10 to the power minus 7 square divided by partial pressure has to log 10 to the power minus 14 minus log of pH2 is equals to minus 0.258 divided by 0.0522. This becomes 14 plus log of pH2 equals to 0.258 into 2 divided by 0.059. This is 8.7. So this becomes log of partial pressure S2 is equals to subtracting 15 from this minus minus 5.26. Okay. So pressure of H2 is equals to 10 to the power minus 5.26. I can write this as 10 to the power minus of 6 plus 26 74.74. So 10 to the power 0.74 to 10 to the power minus 6. 10 to the power minus 4. 0.74. Yeah, so approximately 5.49 into 10 to the power minus 6. Yeah, 5.4. So 5 point something will be correct. 31. And also far, I think these solutions. Oh, there's one normal, so mm, I'm trying to find the solution. So normality is given as molarity into n. N is the number of equivalents. Okay. Um, I have more intuitive feeling of H plus 2, like H2SO4. If it's one normal H2SO4, you get 2 H plus. If it's 1 molar H2SO4, you get 1 mole of H plus 1 normal H2SO4. That means that uh, plus ion concentration. Since you get the 2H plus 2 divided by the electron transfer number here, 2, let's say 1 normal H2SO4, you get 1 mole of H. 1 normal H2SO4 gives 1 mole of H plus. How do I just write for basicity? Okay, this definition. So molarity and given as normality and divided by n. So normality and molarity, n here is the number of equivalents. So to determine this, for acids, n is equals to number of protons and for acid, n is equals to number of H plus. For base, n is equals to number of OH minus n. For any other redox reaction, n is equals to number of electrons transferred. Transferred. So we are given normality for nickel just to electron as we can right. So molarity देखिए molarity calculate करेंगे. So molarity normality was given as 1 and since the charge transfer number of electron transfer was 2, so the molarity. Next question is a copper storage tank contains dilute sulfuric acid at pH 0.1 is blanketed with hydrogen at 1 atmosphere. Calculate the maximum zero copper ion concentration and combination of acid in moles. This is molarity metal and moles per liter. We have to find molarity of copper plus 2. What is the corresponding contamination if the hydrogen partial pressure is decreased to 10 to the power minus 4? And what can be the concentration if acid is exposed to 10 to the power minus 4 atmosphere of oxygen? Even the pH is equal to 0.1. We can calculate the H plus ion concentration. H plus ion concentration equals to 10 to the power minus 0.1. Then this becomes minus 0.1. 0.794. This is H plus ion concentration. We're given partial pressure of H2 is equals to 1 atm. Standard potential for copper reduction. Volts. And yeah, I think the first part is information is enough. Copy this. Mhm. This is given. First equation for the copper. So copper dissolution will take place until both cell potential become equal. So E cell for Cu becomes E cell for hydrogen. Copper half reaction is Cu plus 2 electrons at Cu and twice H plus 2 electrons give you H2. For the copper half, half, the next equation becomes not not C Cu plus 2 Cu plus 0.0591 divided by 2 log of Cu plus 2. This becomes equal to E naught plus H2, which is 0, plus 0.0591 divided by 2 log of H plus ion concentration square divided by pH2. So this is the everything. Now just need to put the values. That's 0.34. Uh, wait, 0.34 plus 0.0591 by 2 log of copper ion concentration, which we have to find, which is 0 plus 0.0591 divided by 2 log of H ion concentration we calculated, 0.7943 square divided by partial pressure of H is 1. So this becomes log of 3 plus 2 is equals to 0 log 0.7 square into 2 divided by 0. This minus 0.34 into 2 divided by 0.591. 0.5. This we already know, right? Log of is 10 to power minus 0.1. Yeah. Minus 0.368 0591. 0.68 divided by 0.0591 equals to log of 10 to power minus 2 minus 11.50 yeah, 0.2 minus 11.50 plus to minus 11.70 so copper ion concentration is equal to 10 to the power minus 11.70 to 10 to the power minus 0.3 sorry, plus 0.3 plus 0.3 minus 12 10 to the power minus 3 into 10 to the power minus 12. This comes out around 1.99 into 10 to the power minus 12 more. Next part is similar. Same up to here. And this equation is same. we're just changing the partial pressure of hydrogen gas, right? In the question. So what is the partial pressure of hydrogen is reduced to 10 to the power minus 4. So what will happen is, instead of 1, here you get 10 to the power minus 4. And you again solve this whole thing. You should get Cu plus 2 equals to 8.29 to 10 to the power 27 mole. Now for the third part, we have different reaction taking place. So we only consider the oxygen reduction reaction here, which is O2 is 4H plus 4 electrons gives rise H2O. Here we are given partial pressure of O2 is equal to 10 to the power minus 4 atm. So, and E naught or O2 O2 is equals to 1.23 volt. Again, left hand side remains the same. That's what we are trying to find, the copper and concentration. Right hand side becomes little different. In this case, it's standard reduction potential is 1.23 plus 0.0591 divided by 4 this time, since 4 electrons are transferred, log of H plus ion to the power 4 multiplied by partial pressure of O2. So this you're given plus ion concentration, let's just 0.34 log of Cu plus 2 equals to 1.23 minus 0.34. This will be multiplied by 2, right? 2 times into 4 divided by 0.0591 plus log of plus 4 into partial pressure of O2 is equal to 10 to the power minus 4. Log of Cu plus 2. This value becomes 1.23 minus 0.34 into 4 divided by 0.5. This is 60.2 divided by 2 plus half log of What was it? Plus, if I take it 1 atmosphere, then this becomes 10 to the power minus 4, 30.1 plus minus 2, 28.1 plus 27.9. So copper plus 2 ion concentration equals to 10 to the power 28.1. Did I make some mistake? Answer should be this. Cu plus 2 equals to 8.29 into 10 to the power 27. I think, yeah, this is taken as 1, right? 10 to the power minus 4 loge to this value will be way lower. Second part है 14. 10 to the power minus 4 to the power 4 into 10 to the power minus 4, 10 to the power minus 20. This would become 30 minus 20, so 10 then H plus ion concentration. pH was point. H plus ion we calculated was 0.1. No, no. Yeah, so put that value here. Then you should get the correct value. I assume this H plus has 1, so okay, I think you guys can do it. And let's go to the last question. Calculate the theoretical tendency of nickel to corrode in volt in deaerated water at pH 7. Assume corrosion products are H2 and nickel hydride. The solubility product of which is this. Okay. So we're given nickel plus twice H2O gives you nickel hydride plus H2O. This is the equation we are assuming. One nickel plus 2 electrons gives you nickel and not this is given as minus 0.25 volt. Solubility product we are given nickel plus 2 OH minus or twice for this nickel hydride. Okay, into 10 to the power minus 6. Concentration of nickel plus 2. Since pH is 7, HN concentration is 7 is equals to OH minus ion concentration. So 10 to the power minus 7 square is equals to 1.6 into 10 to the power 16. Nickel plus 2 ion concentration is 1.6 into 10 to the power 2 whole. So E is equals to E naught plus 0.0591 divided by 2 into log of nickel ion concentration. So just put the nickel ion concentration here and we'll get the potential. So minus 0.25 plus 0.0591 divided by 2 log of 1.6 into 10 to the power minus 2. This should come about 0.303. Okay. Okay. Any doubts in these last two questions? If not, we can end the session here. You can always email me your concerns and then yeah, try to respond. So if not email, otherwise you can also ask the questions on the member form. Okay. Thank you all for attending. Bye bye.